Okay. So the reaction is the same as before. We noted that we have what I call coupled reactions. What we're trying to do is get this compound in solution. And we're going to couple that with this reaction. We're going to take silver ions and combine them with ammonia in solution and produce this complex ion. Oops, excuse me. That's a plus. So we still got this charge here over there. Okay, this is in solution also. Okay, so what we're after is the Kf for this reaction. What's the formation constant for this reaction? So eventually, we're going to answer this question. That question. And for completeness, we're still dealing with this one in solution as well. KSP. All right. So how are we going to do that? Well, both of these reactions are going on at the same time in that solution. In other words, we've got this one initially, right, as silver nitrate. So we've got these ions in there, silver nitrate. And then we're going to combine them with ammonia. Right? So the sequence of the steps in the reaction are, we're going to have free silver ions in solution. We're not going to have any of this. But we're going to have free ions of silver in solution. And we're going to combine those with ammonia to make this complex ion. So at the beginning of the experiment, we have created this complex ion, and that's all there is in solution. Well, this plus that plus that. We don't have any of this in solution. So what we're going to do is, in order to find out this value, we're going to titrate this solution. Let's see, do we use HCl or sodium chloride? Potassium chloride. Yeah, sodium chloride would work too, but potassium chloride is good. We're going to use potassium chloride and titrate this solution until the Q exceeds the solubility product. In other words, we're going to increase this one until the Q for this exceeds the solubility product. And at that instant, it will form some of that. And it's so difficult to see with the lights on that by the time you see it, you've gone past the equivalence point. So that's why we turn the lights out and just have enough light in there so we can operate the burette. And we're looking for the appearance of this, first appearance. And that's why we use the Tyndall effect, because that is much, much more sensitive to see the formation of this product in solution. Okay, so that's the titration part. And once we get that information, then we'll have we will have this concentration here, because we're delivering a known concentration of potassium chloride into our reaction mixture. And when we get to the known concentration and a known volume, we can calculate the number of moles required to reach that point. Okay? So that's the titration that we're doing. It's not an acid-base titration. Well, actually, it's not an Arrhenius acid-base titration. It's a Lewis acid-base titration, to be honest with you. Okay, so how do we simplify this process? Because once we got that information, what do we do with it? Well, here's the simplification. Notice that we have the similarities between these two. And the reason we can do this is because both of these reactions are happening at the same time in that reaction mixture. Right? Both of them are going on at the same time. So what we're going to do is solve this KSP for silver. Right? And that means the KSP divided by chloride. Okay? That's what we did with this one. Now we're going to plug in the equivalence of silver here, this value, in for that silver right there. Okay? So now Kf equals the complex ion divided by the equivalent of our silver, KSP, divided by chloride, times ammonia squared. Okay, now we've got an expression for all of it together, and what we need is, at the equivalence point, we need to know the chloride concentration, the ammonia concentration, and the complex ion concentration. But if we resolve this, the denominator of the denominator is the numerator. So we take this one, ASP, and put it up here, right there. Okay, so that's our equilibrium expression for determining this. We just have to say how we're going to find each one of these. Well, this is given to us, KSP. Right, we know that for this one right here. We need to calculate each one of these. Right, so how do we do that? Okay, so that's where the data treatment calculations come in. All right, in order to make sense of this, what we need is we need an ice table, but it's not your traditional ice table. Let me go up here. Rather than use concentrations, we're going to do ice in terms of absolute amounts. And then we're going to backtrack and calculate concentrations that we can plug in this formula. Right? So that's what this example is for here. And in order for the ice table to make sense, we have to break out this KSP again as silver and chloride. So we've got this one still, got this one, and we've got this one, silver, chloride, and then ammonia. Okay. Now, if we use this to set up our ice table, it will look like this. Let's see. Usually we have a product over here. Actually, it doesn't matter. I'm going to do it this way. If we're going to say that's the KF, then we should put this one on the right and this one on the left. So this would be silver. I know the method, the hard copy doesn't show it this way, but the result is the same. And then we have chloride here. And then we have, and I put those squiggles rather than the equivalent sign, or rather than an arrow or a double barbed arrow. So here we have silver. Actually, I'm off screen now, aren't I? Okay. Let me move back so we can pick up the whole thing. It's going to go way outboard. Okay. There we go. I'll just have to move my camera around so I can pick everything up.
It's all right.
Okay, now we have silver, and then we have ammonia, and then we have chloride. So, set up this way, we have, these are the reactants and these are the products. Those are the products, these are reactants. So we need absolute amounts. If we have, let's see, 5 milliliters of 0.1 molar of silver nitrate. I'm checking to see if this is actually what we're going to do. Yeah, 5 milliliters of 0.1 molar silver nitrate. So that gives us this one. And multiply those together, and hold on a second. Ice change. That would give us 0.5 millimoles. Remember millimoles? I'm going to use millimoles because it's more convenient. We just multiply molarity times milliliters. So 5 milliliters times 0.1 concentration of silver gives us this. And then in solution, we're also the first go round, the only one that we're going to do is 5 milliliters of 1 molar. So we're starting off with 5 millimoles of that. And then the chloride is determined in the experiment. So the example here, I just said, well, suppose that it takes 1 milliliter of 0.1 molar KCl. So this is from KCl, 1 molar, 0.1 molar, excuse me. Right. And we use 1 milliliter of that. So that gives us 0.1 millimoles. Okay. And in the beginning, we're saying none of that, none of that. So when we reach equilibrium, what we're saying is we're removing all of this silver to make silver chloride. So we're subtracting this amount, millimoles. And since this is a half, and the ratio is 2 to 1, 2 of these, yeah, 2 of these for every one of those, and I just walked off screen again. That means this one would be 1 millimole. Okay, so if we're using up all that, we have to use up 1 millimole of this because it's 2 to 1. Okay, and we're also using up all of the silver. It's all gone. Now, excuse me, all the chloride. All the chloride is gone. So the equilibrium situation is here is 0, here is 4, and here is 0. So what's going on the other side? Well, if we're using all that up, it appears over here 1 to 1 plus 0.5 millimoles. And if we're using up all of this, it appears over here plus 0.1 millimoles. Okay, so now we have 0.5 millimoles and 0.1 millimoles. That's at equilibrium. See if I got all those right. Yeah. Okay, now in order to do the calculation, we have to know the concentration. Do we have enough information here? Let's see. We have chloride at equilibrium. But we're going to use this one to do the calculation. This one was to set up our ice table. Right? Well, we're going back to this one to do the calculation. KSP, then ammonia at equilibrium is 4 millimoles, and chloride is 0.1 millimoles, and the complex ion is 0.5 millimoles. But we need to know concentrations. So we got to say, what's the final volume? Well, the final volume is, we started off with 100 milliliters, correct? Let's go back and look. Yep, volume of solution after dilution, right? Each flask, this is on page 2, each flask is then diluted to 100 milliliter mark with distilled water. Okay, so that's the starting volume before we add any potassium chloride solution to it. How much did we add? 1 milliliter. So the final volume is 101 milliliters. 101 milliliters. 101 milliliters. Millimoles divided by milliliters is molarity. So this one, ammonia here, 4 divided by this is 3.960 times 10 to the minus 2 molar at equilibrium. This one is, divided by that, is 4.950 times 10 to the minus 3 molar. Okay. And this one, 0.1 divided by 101, yes. This one is 9.901 times 10 to the minus 4 molar. Okay. Now we have those three values. We got this one, 4.950 times 10 to the minus 3, chloride, 9.901 times 10 to the minus 4, and ammonia, 3.960 times 10 to the minus 2. And then our KSP, which is 1.7 times 10 to the minus 10. I think Salcon uses 1.8. So take your pick, whichever one you want to use. It's weird the way these solubility products, it just depends on who measures them. And if we put those values in here, then the calculation of KSP, KF, is 1.84 times 10 to the 7th. Or actually, we'd have to round it off because there is only one significant figure here. So 1.8 times 10 to the 7th. And then you compare that to the accepted value, which I believe is 1.8 times 10 to the 7th. One second. I want to be sure I put it in here somewhere. KF, that's KSP. KF, where's KF? Gotta be in here somewhere. Well, I'm probably looking straight at it. Don't see it. I know where it'll be. A handout. It is complex ions. Silver, ammonia. It is ammonia, silver, ammonia. 1.6 times 10 to the 7th. Accepted. There you go. Well, that's accepted for this author. Okay. So you would just compare these two. You know, do your percent error. There you go. So what I tried to do is make sense of the procedure. So it's, you have sort of a feel for what's going on while it's happening. Okay, any questions? I've probably talked enough for today. If that's the case, then I guess we're done for today.